Is it working? Thank you very much for coming to the seminar. I am going to introduce Takemasa, and I shouldn't need a piece of paper because I am very proud to say that I was his advisor. But he has gotten so many prizes after that I probably will need to cheat and look at this. But I would like to say Takemasa was very kindly given 2 years to get a master's at the University of Maryland, and when I started working with him, I thought, wow, he's so good that I told him he should work hard and try to complete a PhD in those 2 years, and he completed a master and a PhD, and went on to other triumphs. He was selected as an assistant professor a few years later, and then he was invited by an organization in RIKEN, which were the largest scientific centers are in Japan, and where they have a supercomputer K that is going to be eventually replaced by another even stronger supercomputer. So he was asked to direct, organize first, and then direct a data assimilation group. And he quickly gathered about 15 super, very good scientists, many of whom have done their own PhD with Takemasa as their advisor, and he got some incredible prizes like in Japan they have a Yomiuri gold medal that is awarded every year to only 3 scientists for any science, and he got that in 2018, which is amazing, and also got the top most prestigious award of the Meteorological Society of Japan. And well, and when he, after 5 years, his group was reviewed, then he didn't get outstanding, but he got extremely outstanding as a review. So, I'm not going to say more, except that I would like to cite what Craig Bishop told me. Craig Bishop is one of the best leaders in data assimilation, and he just went back from the Navy to Australia, and he told me Miyoshi is breaking every barrier in data assimilation science, and that's really true. So let's hear about what you are doing.
Thank you very much. Thank you very much for many people coming to this seminar. So today I'm going to talk about what we have been doing in RIKEN, that's a research institute in Japan. It's what we call big data assimilation, new science for weather prediction and beyond. So let me first briefly introduce. Okay, this was working, but not now. Okay, okay, good. So first, introduce myself. Although Eugenia, thank you, Eugenia, giving a very nice introduction. So as Eugenia said, So I spent 2 years at the University of Maryland, but before, as a graduate student. But before that, I was a JMA employee. JMA is the weather service in Japan. Right after I graduated from Kyoto University. So I didn't go to a graduate school in Japan. Instead, I started working for the government. This is the time when I started developing the 3D bar system for mesoscale, new mesoscale system at JMA. So that was in 2002. And then I had a chance to study at the University of Maryland with Eugenia in 2003 for 2 years. So their requirement was to get a master's degree in 2 years, but as Eugenia said, I finished a PhD. Then I went to JMA again my research for PhD was about the ensemble Kalman filter, and I started the development of the ensemble Kalman filter with the Japanese operational numerical weather prediction system. And then was 2008, the end of 2008, I decided to go to Maryland again as a faculty member. And I spent for 4 years, exact 4 years, and then I again went back to Japan. This RIKEN is a research institute in all sciences. So they are strong in physics, biology, and chemistry. They are not strong in geoscience, any geoscience. But I started this data assimilation research team, mostly focusing on geoscience. There's another research team focusing on the model development, or weather model. So we are the only 2 groups in RIKEN. RIKEN has 3,000 scientists, and our 2 has maybe 20 or less working on geoscience problems. So I have been leading this data assimilation research team in RIKEN Center for Computational Science, where we have the largest supercomputer in Japan. And the scope includes not only meteorology, but also broader applications of data assimilation. That's why I'm going to talk about meteorology, but beyond meteorology. Okay? So this is a computer that we have. This is already 8 years old. I think the age of computer, like this high-end supercomputer, is like 1 year may corresponds to like 10 years of human life. So 8 years old, meaning 80 years old in human life, so it's time to retire. So they already decided the date to retire. That will be, I forgot exactly the date, but it's middle of August this year. So this has a life less than half a year from now. So when I went to Japan 6.5 years ago, it was still new, like 10 or 20 years old in human life, and really the fastest was #1 supercomputer. And I was thinking, because my job at that time is to think about how to use this computer and to make something new. Because this is old now, we are planning to develop the next one. So after this retires, we will start implementing the next one. That will be as powerful as 100 times of this supercomputer. So we are now waiting for that. Okay, so this is my group. Now we are a group of 14 scientists working on various problems of data assimilation, but mostly focusing on numerical weather prediction because of my background. So again, I thought about how to use this computer. My colleagues in RIKEN had this simulation in 2012. And this is a global model at 870 meters resolution. So this is still the highest resolution, even though this simulation is like 7 years old. I think that there are people trying to do higher resolution simulation, but still this is the highest resolution. So that if we have the next generation computer, I believe that we will have even higher resolution global simulation. Okay. This is great. And this is 870 meter resolution. It's already published in 2013. On the other hand, we have new technologies for the observation. This is the actual image from a phase array radar. So this is three-dimensional image. Every 30 seconds they take the whole sky scanning. So we get this every 30-second image, almost like a smooth movie. This is really amazing. So this is a phase array. So we take 100 vertical levels simultaneously, while the regular radar like this takes only one level. That's why we get 100 times of more data. So we have a big computer. So the question is how to combine these two. So that's what I thought at first when I had this new data and also the large supercomputer. So data assimilation is something to connect the observation and the model. So we have a high resolution model and this 100 times of more data. So we combine these two and process all of these big data with this supercomputer. So that's what we call big data assimilation. So every 30 seconds we get the data, and every 30 seconds we assimilate the data into the model. The model at 100 meter resolution. And we run 100 ensemble members to represent the uncertainties. So we have a range of uncertainties and we get every 30 seconds. So this is a case that we tested. The first, one of the two first cases that we tested this system. So I saw this image on September 11th, 14. I live somewhere close to this dot and my office is there. And I biked to the office for 30 minutes. And I looked at this image from JMA, that's weather service, and I decided to bike. As you can see that this developed very quickly. And in 30 minutes it became like this. So I'm a PhD in meteorology. And I'm supposed to be a good weather forecaster. Well, it's impossible to predict this rapidly growing system. And this affects a lot of people living in Kobe. This is a big city, 1 million people living in this area. So this has a major impact in the city, although there was no disaster reported. So that's why we chose this case for this testing this system. So we simulated this heavy rainfall system. But we also have the observation from the phase array. So every 30 seconds we have the observation. So we start at 8:01:0, and every 30 seconds we get the observation. And this data is assimilated into this simulation. So this is all the others are from the computer. And this is a simulation without the data assimilation on the bottom left. So this will move. So we have this, but it takes time to catch up. So it takes time like 20 minutes to catch up. But every 30 seconds we get the data. That's how we can catch up. So without the data, we have no predictability at all. We cannot predict this type of event if we update the state every hour. But every 30 seconds we get the data and we just feed the data into this system. Then we get this really nice structure of the observed precipitation system. So the red part corresponds to more raindrops, heavier rain. And blue part, the less reflectivity. That means we have fewer raindrops. We can also see these clouds. The clouds are invisible from the radar, so the radar not sensitive to these small droplets. But we can see this because the simulation contains all variables. So we can even try to fly in, even though we cannot do that in the real world. So that's an advantage of the simulation. Okay. So this is nice, and I will not play the whole movie, but this is available on YouTube. And this is now ranked number 6 of RIKEN channel. The RIKEN channel has more than several thousand contents. And this is ranked number 6. I'm very happy about that. So if you can kindly click, increase the digit, probably the second digit. Try to beat the higher rank. Okay. So again, the observation have some noisy patterns because we have noisy observations, or we may have some missing values. So the observation may have some missing parts, but the data assimilation can interpolate those missing parts or the noise, smooth out the noise. So we have a nicer pattern. We assume that these are closer to the real world than the observation. And without the data assimilation, we cannot predict this event at all. So this worked very well for this case. And we tested in other cases, and all the cases showed very promising results. So we are very happy about our results. So people might ask if this kind of prediction for the next 30 minutes or so will be useful or not. But we had this event actually happened in Kobe in 2008 in summer. This river like this became like this in only 10 minutes. This is the actual picture. And this became like that in 10 minutes, and some people couldn't escape. And 5 people unfortunately died in this river at that time. So if at that time we didn't have any warning system in the river. After this event, the Kobe city government implemented some sirens and warning systems. But we need to have prediction to make it more useful. So even if the prediction 10 minutes for 10 minutes will be useful, it's really a matter of the life. Okay. So the data assimilation is like a bridge connecting between observations and the numerical models. We add the value. So what is important here is the simulations based on the process. So we describe the process as the equations of motion, and then we solve it in the computer. That's how we can predict the future. So this is process driven. And observations provide the real world data. So we need both. And each has different strengths. So data assimilation tries to combine this data-driven approach and process-driven approach. So without the process, we can just learn from the data, and we can build the data-driven model to predict the future. But that cannot predict the extreme events, because there's no experience in before. Then there's an extrapolation of the data-driven model usually doesn't perform very well. So the process can produce something that we have never experienced before. So this is the idea of data assimilation. Shuji-yan and Eugenia and other people proposed a very nice idea to combine both the idea of chaos synchronization and data assimilation. And I really like this concept of chaos synchronization to describe what the data assimilation does. So we have a nature system that we don't know perfectly, we cannot know perfectly, but we have some understanding of the nature. And based on our understanding of the nature, we can build a model. So we have a model to mimic the nature. And we have some limited information transferring from the nature to our model made by the observation. So this is also not perfect, that the observations should be noisy and also imperfect. So the question is if we can synchronize the behavior in the model to the actual nature. So that's what we have been doing in weather prediction and other applications. So this problem of synchronization is equivalent to understanding the stability of this synchronized state. So we have a nature moving and we cannot control. Let's assume that we cannot control the nature. But we have a model that we can play with, and then we have some information passing from the nature, then we synchronize the behavior of this model to the nature. If we can synchronize it, we have a better estimate of the nature, and also we have a prediction of the nature. So we cannot control the dynamical instability of the nature. So this tries to separate these two. But we can control our observation system. So what I showed in a moment before was the very rapidly growing system, weather system, the convective weather system. So that grows very rapidly. So even 10 minutes is long. So that's why we needed to have very frequent observations. So we assimilated every 30-second observations. So that was good for the rapidly growing system. But for the synoptic weather, once in 6 hours or 12 hours will be good enough for synchronization. So it really matters what kind of dynamical instability or what kind of the chaotic dynamics that we are trying to predict or estimate. And then we need to design our observation accordingly. So if you have rapidly growing system, then a rapidly changing system, then we need to observe more frequently and more densely and more accurately. So that's how we can make these two coupling strongly. Okay, so this is a general concept of chaos synchronization. I didn't know what kind of audience today, so I prepared some simple example of synchronized chaos through data assimilation. So let's consider this simple system. So this n, let's assume that this is time. So time n to n plus 1, this is a model. So if we give some number here, we can compute this given a is 4. So if we give 0.2 here and a is 4, then we can compute that the time 2 will be 0.64. And then we can compute the next one and next one, like this. And we can do the same thing for this different time series. So this is a small noise added to this 0.2. And if you look at here, for example, 15, the time step 15, so it's 0.00009, so it's almost 0. But here it's 0.05. It's very different. So if you make the plot for this blue time series and red time series, the red is on top of blue. So we see that the red is really on top of blue for the first 13 time steps. But after that, it starts separating. So this is the nature of the chaotic dynamical system. So that's what happens in the weather system. So the question is if we can synchronize this red time series by transferring some information from this blue time series. So if we transfer the perfect information from this blue to red, then we can make perfectly the same time series as blue because we have no error in the model, in the process. So what we do what I did is to have some noisy observations so that we have some degraded information transferred to this red time series. So let's see that these blue curves exactly this time series, and these circles here are the noisy observation of this time series. And then we just tell these noisy observations to this red using the Kalman filter. That's a kind of data assimilation method. Then we can make this red series closer to, well, on track to this with this blue curve. So this is how we make this system synchronize with the nature. So we assume that blue is a nature. Okay. So the advantage is that on average, this red is closer to this blue curve than the observation. So the observation noise is larger noise than the error in this red. So that's how we get a better estimate using the data assimilation. Okay. So what we did is to predict using this process. That was a simple equation. And then we get the noisy observation and combine them. How do we combine them? So we consider the errors. So this is the Bayesian estimate. So I think that data assimilation is all about the errors. So we need to think about the errors. So if we can quantify the errors like this for the forecast and also the observations, and we can combine these two independent information to get some merged information. So that's what it does. Okay, so we consider the errors. So the errors we can describe in a probability density function. So if we have the forecast value here, then this is a probability density. We can write the probability density like that if we know the shape of this probability. And we can do the same thing for the observation. Then what we do is just to multiply these two basically and normalize. So that's the area will be 1. That's the action of probability. So we get a better estimate. It's even more accurate than A or B, and it's higher probability. So that's what we do. So if you assume the Gaussian PDF, the Gaussian function is like this, so A and B, and we know the sigma, that's the width of this Gaussian function, and then we just multiply, then we can compute. So the multiplication of two Gaussian functions will be the Gaussian. So if things are in Gaussian, if we have a new observation that is Gaussian, then we can do the same thing to get another Gaussian. It's getting narrower, more accurate. So we have the new estimate for this center value and also the width. So if the things are Gaussian, then we can keep all in the Gaussian frame. So that's the beauty of the Gaussianity. Once we have non-Gaussianity, things will be non-Gaussian forever. So that's the real world. But we can approximate the PDF. The Gaussian approximation works for most variables, not for some variables. Okay, so what we do in numerical weather prediction is that we try to predict this true atmosphere that is unknown. So with some estimate, we can predict, and if we keep forecasting, the forecast will go apart from this nature. So that's the chaotic nature. So once we take the observation, we combine these two to get a better estimate, and then we forecast again. And we repeat this process. This is known as the 4-dimensional data assimilation, because if we consider this analysis, this is the result of the data assimilation of this observation. So this includes this observation. But how did we get this forecast? This forecast coming from this, with this observation. Without this observation, we get the forecast like here. That's what we could do best. And then we never get this. So we get this because of this observation. Otherwise, we have some forecast somewhere there, and even if we use this observation, our estimate will be somewhere here. So that's why we accumulate the observations in time. So all observations contained and then propagated in time through this model. That's how we use the process-based model. The process can propagate the information, observe the information in time. That's how we get the beta estimate, and that's how we make the weather prediction accurately. Okay? So we have the initial state and simulate the weather or whatever system it is. We can simulate, and then we get the simulated state combined with the observation through DA to get the best estimate. Okay. So if we open up this black box of DA a little bit, then we can see that we need to match the variable between this and the observation. So this is the model simulation. So we have the variables in the model may not be the same as the observed variable. So if we consider the example that I showed at the beginning, that's the radar reflectivity. The radar reflectivity is the result of the reflecting signal of the radio wave. So the radar emits the radio wave and observes the reflecting signal. We don't simulate the reflecting signal here. So what we do is to simulate the radar in this simulation world. So this is a modeled atmosphere. So we have the raindrops or other things, temperature, humidity here. And then we put the radar in the simulation and observe this simulated state. So what we do is to compute the radar reflectivity from this variable to what is observed. So the same for the satellite observations. So we observe the infrared radiances, for example. Then we have no infrared radiances here. So what we do is to simulate what will be observed if you have this simulated state. So we have a model state and we observe. So we need to simulate the observation, like the radar simulator or satellite simulator. So then we can take the difference and we try to minimize the difference through the data assimilation process. Okay. So what we can do with data assimilation, now we can do many things. So first of all, we can make a good prediction, or we can estimate the state. But I think that what was very important in geoscience about data assimilation is what actually Eugenia showed in the 90s. So she and colleagues at EMC made this time series for the past 40 years of the estimate, best estimate of the atmosphere. That changed the whole climate science because the people use those data to understand the climate dynamics and all. So that all started from this application of data assimilation. Why that was so powerful? Because of this integrate the various data. So we have satellite observations or many different types of observations, but all fit into this state. And this state is the model variables. The model is designed by humans. So we have very good structure of the data. We have gridded data for all variables that we understand, and that is in this state for the model. But the observations are more random. It's different types of observation have different variables to observe, and it's hard to analyze. So we can analyze each observation separately, but if we combine all observations together, it's going to be very, very difficult. But this data assimilation process can get all the observations into this state. So that's what the reanalysis or the analysis did. So this is really powerful. And I think that's the highest cited paper in all geoscience field. So because it was so powerful. And we can also now do the model error or bias estimation and correction, or the parameter estimation, or even model identification. I mean that we can try to minimize the difference. So between the observation and the simulation. So once we forecast, we can compare with the observation. We always monitor the differences in data assimilation. So this is inputs to the data assimilation. So we can identify the systematic differences. So if the model is imperfect, we can add some new term based on this experience. So that's more like data-driven, but the data-driven approach can also provide something here. So that's something ongoing recently. Okay, so what we did using the K-computer for the next generation big data simulation is something like this. So we had the new generation sensor, Himawari 8, that's a new geostationary satellite. And this work was done by Dr. Honda in my group. So Himawari 8 is like this. So the left side is the previous generation, the right side is the new generation, Himawari 8. And it's more frequent, colorful, and precise, and has 50 times or more data than the previous generation. This is another new sensor producing orders of magnitude more data. So both of these are generated in the computer. So these are the computer simulation. So we have a typhoon here. This was the strongest typhoon in 2015. It's Typhoon Soudera. And we have a typhoon structure. But with assimilating Himawari 8, we get these clouds pattern a lot different from this. Okay, so we assimilated all sky infrared variances. And this is the infrared variances observed by Himawari 8. So these two are generated in the computer. So this is a simulation, and also the Himawari simulator can simulate this infrared variances. Okay, so this is much closer to this. That's good. So it worked very well. And every 30 seconds or every 10-minute data assimilation can make some difference. So we can see slight difference, but it's harder to see the difference. Okay, we have thicker and higher clouds in 10-minute cycle, and that was observed. But less here, or some ice structure here, it looked differently. And 10-minute cycle is closer to the observation. So the 10-minute cycle means that we assimilate the Himawari data every 10 minutes. So this made a lot of difference in the intensity prediction of this tropical cyclone. The tropical cyclone intensity is one of the hardest problems in meteorology. So the blue shows the best track. So that's what is analyzed based on the observation. And black is the case without any Himawari data assimilation. And green is every 30 minutes, and red is every 10 minutes. And as you can see that this rapid intensification period made this tropical cyclone the strongest in the year. And we can predict, these thin lines are the prediction. The thick lines are the analysis. So the analysis is the result of data assimilation. So the prediction provides like 12-hour prediction or longer prediction can provide this accurate intensity prediction compared with the 30 minutes. So the 30 minutes still helps, but not quite. So what we found is that this rapidly updating system really helped in this case. We also explored the ensemble simulation of the global weather, but large ensemble. So we have this 10,240 ensemble members, ensemble gamma filter, that's a data simulation. So each individual dot represents the atmosphere. And if you look at this 16, you can see more similarities in the northern hemisphere, more differences in the southern hemisphere because we have more data in the northern hemisphere. So why this is important? Because as I said, data assimilation is the theory of errors, and it's important to how to represent the errors. So we represent the errors using the samples. So that's what the ensemble Kalman filter does. So using 100 samples, 100 members is a typical choice because one sample requires a full simulation. That's expensive. So usually 100 simulations is expensive enough. And we try to do all the data assimilation and the error estimates using the 100 ensemble members. We still have lots of noise. So this shows correlation patterns from this star. The correlation means that if you observe the star, this observation will have an impact like that. This is like continental scale or even global scale, and it's spreading out everywhere because of the sampling error. So that's a big trouble in the ensemble Kalman filter, and we have methods to localize this, but then we limit the impact of this observation only surrounding like less than 1,000 kilometer area. But this is like 10,000 kilometers away, and we found that this was a surprise to us, but we found that we have significant correlation even with 10,000 ensemble members that affect 10,000 kilometers away from this observation. So the question is, what's the impact of considering that long-range correlations? So this shows the root mean square errors. We have a lot of lines, but we just focus on this black and red. The black is the case with 80 ensemble members. So with 80 ensemble members, we had to localize the impact of the observation within a surrounding area. And that worked very well. And it's produced the forecast error going like that. So this is 0-day forecast error, and 1-day, 2-day, 3-day forecast error going like that. So that's reasonable. And if we have 10,240 ensemble members, like this red curve, we remove the localization because we have large enough ensemble. So the sampling error is negligible. And then we get this red curve. So this forecast error, 1-day forecast error, is equivalent to 5-day forecast error. So this is an idealized experiment. So this doesn't tell us that in the real world, if we run 10,240 members, we may not get this much advantage. But still, even for the idealized case, we get this huge impact to extend our predictability. So that was our surprise. And this was published in this IEEE journal Computer as a cover feature. So if you're interested in more details, it's a November 15 issue. Big ensemble data assimilation in numerical weather prediction. This was part of our big data assimilation effort. Okay, so what we have been exploring so far is to combine the big data from the real world with the big simulations. So we push all the limits in numerical weather prediction. That's one is the ensemble size. We tested 2 orders of magnitude more ensemble size. And rapid update is 30-second update. Usually hourly update, it's 120 times more rapid. And also high resolution. Usually it's 1 kilometer resolution considered as a high resolution mesoscale weather prediction. And we did 100 meter that has 100 times more horizontal grid points. So all of these are 2 orders of magnitude more than the current systems to explore the future numerical weather prediction. So the most recent achievement are related to this timeliness. So we explored how to improve the forecast accuracy, but also the computer speed. Because we have the system to update every 30 seconds. We need to show that our computation is completed within 30 seconds. At first, when we developed the system in 2016, it took an hour, more than an hour actually. It failed within an hour, so it took more than an hour. And then after 1 month of the development, we accelerated quite a bit. And in 2016, we achieved about 10 minutes. But we needed to complete the computation within 30 seconds. 10 minutes is too slow. It's still 20 times slower than the goal. So last year, we spent quite a bit of effort to improve the computational time. So with a 100-meter mesh, we reached like 70 or 80 seconds. that's still slow. So we decided to degrade the resolution to 250, then finally we reached this 30 seconds. So this is the 30 seconds. The 30 seconds is only here. But on the right, last year in June, we computed this within 30 seconds. So the question is if 250 meters is good. So we compare the forecast at 250 meters or 100 meters. This is the actual observation. So this is the analysis. The analysis looks similar. 5 minutes forecast, 10 minutes, 15, 20, 25, 30 minutes forecast. So we would like to run the 30 minutes forecast at this moment. So this is the longest forecast. And well, we see some differences. They are missing small details and also some differences, but not a major difference. So we are happy with this. We can do this prediction at 250 meter resolution every 30-second update real time. So that's what we proved. Good. So for every 30-second update, we cannot use the K-computer real time because K-computer is not a dedicated machine for the weather prediction. So what we did is this simple system, the nowcasting. But this is a three-dimensional nowcasting that we consider the dropping motions or the ascending motions. So this produces the time series like this, so it just moves, but this has a scale for the 10-minute period. So we now have this system real time, and using this smartphone app. It's MTI, that's a private company developing this smartphone app. It's already 150,000 downloads, and people are really using in those areas. So it's nice. And this has a scale compared with the persistence, of course. The persistence is just, it doesn't move. So just moving it can make a lot of impact. This is a thread score. Thread score is always higher for 10 millimeter per hour or 30 millimeter per hour. It's higher than the persistence. So this has a scale. And we get a feedback from the users, and those are good. Okay, so we try to improve this system using the the recent advance of machine learning technique. So this is a kind of the deep learning method, convolutional long short-term memory, the LSTM. And we applied this convolutional LSTM to this data. Well, I will not go into detail. But this is a combination of two types of neural network structure. One is a convolutional neural network, and the other is LSTM. The LSTM takes the data in time series, so it fits well into the time series prediction. So we feed the data, like time series data, and then we output the time series data. So that's what the convolutional LSTM does. So in this case, we split the area. Yeah, we split the whole area into small areas to increase the sampling size. And we apply this. So this shows basically the advantage of this LSTM. So this is the actual observation. And this is the optical flow. The optical flow is just a motion. And the LSTM is the neural network. And this predicts 30 seconds, 1 minute. And you can see a clear difference between these two, and these are similar. So that what happened was disappearing. So this rain, so this is a vertical section, is dropping and disappearing. So it's disappearing, but the optical flow can just propagate. So the LSTM can capture it from the data, and it has clearly a better match between these two than this. And we have statistically significant improvement by using the LSTM. So we try to improve this nowcasting system using this machine learning technique. So this is the future plans. So we actually have finished this big data assimilation effort for the past 5.5 years. So this March is the end of the period of this project. And then we get the next 3-year extension based on our achievement. They continue funding us to extend our research. So this is the picture. So the idea is to synchronize the cyberspace with the real world. So we get data from the real world through the advanced sensing technologies, and we get it in the cyberspace and synchronize with this simulation. And we try to incorporate the advanced artificial intelligence technologies. So it's really advancing rapidly. So I think it's reasonable to think about taking advantage of those advances into here. And also we try to address the control problem. So the eventual goal of the weather prediction is to minimize the impact from the weather, or we take advantage of the weather situation for a better life or for better economic activities. So we have some activities in the real world, but we can simulate, not exactly, but we can simulate the situations depending on the weather scenarios. So we can have an uncertain forecast, and we can control ourselves. That means that we make the choice, the better choice to optimize our activities. So that's the broader scope. So do I have time?
Yeah, 5 minutes.
5 minutes? Okay. So for the broader picture, so the weather prediction is just a kind of prediction. So we would like to predict many things. That's why still people are using this method, but it's not scientific. So we would like to make predictions based on the science. So that's the concept of the predictive science, or what we call prediction science. So what science has achieved is like these things. So these are based on the prediction based on science. So, for example, this type of prediction is based on the deductive approach. So it's based on the model. The computational science, it's known as the third science, can make a prediction. Or the other type of prediction is the inductive approach. So it's based on experience data. That's what we do, that humans are doing, actually. Now the data science is evolving quickly. And this is a good example that this method is very successful. There are many other examples too. So we have two methods for the prediction. And data assimilation, as I said, combines these two approaches. So we can make better prediction and control. So data assimilation has evolved in meteorology and earth science, planetary sciences. But now it's expanding to different fields like social science or engineering, or biology, medical sciences, and other fields too. So I have been seeing this expansion of the application of data assimilation because I saw many studies at the supercomputing center, that's a flagship supercomputing center in Japan. There are many people using the supercomputer. So what they do is a simulation. But once they have a better simulation, they look at the real nature and try to compare. So that's the entrance to data assimilation. And what happened in meteorology is exactly like that. So I think that we can follow the approach that we developed in meteorology can be applied to many different fields. So we have been working on bringing data assimilation into new areas. One example is this. So we have trees growing in the model. So we have a process-based model so that the tree is growing. So this is a 100-year simulation of trees. And we have the satellite observation. Like MODIS gives us a leaf area index every 4 days. So we set up the model in this Siberia, and this is a data assimilation, and that worked very well. So this was published. If you are interested, you could look at this paper. But this almost exactly the same. That means that we have this forest state in each individual tree matching with this observation. So the goal of this project is to simulate the trees all over the world. That sounds crazy, but maybe interesting. Another completely different example is this press forming. You can see that we have some metal, iron board, and we put something, push, change the shape. So this is the deformation process. We have a model to simulate, but this cannot simulate very well for this type of realistic estimation. So when we press form these parts in a car, we have these problems. So we need to predict how much to spring back after, what's the final shape. So if you have this kind of cracking problem, it will not be useful. So we would like to predict, but it's difficult. So what the automakers do is to experiment again and again. So they do a lot of different types of the press forming experiments. Finally, they have the final solution. So if we can do the accurate simulation, we can avoid all the experiments, and we can do only a few experiments to make sure that it works. So that's something that we have been working. Maybe I can skip this part. Okay. So this is what we call the fifth paradigm, because as I said, this is the third science, that's a computational science, and the data science is the fourth science. So we can make the combination of these to bring the new paradigm in the science. So with that, I have been working with, for example, Dr. Seita. He's a medical doctor, and he tried to develop a system to predict the health and disease of a specific person, like predicting the hurricane track. So if we live this life, then we stay in health, or we get a disease or something, so that we can control our habit or something to make us more healthy. So the problem here is that we have no good model, process-based model for the human health. So it's too complex. That's a typical problem. But we can use some data-driven method to build a time evolution model. So the problem of data-driven model is that it's a black box. We don't understand the process. But we can do this type of whole life prediction purely data-driven. That kind of research is ongoing. But the problem is that it's really difficult to communicate with patients and convince them, because we cannot just say that we have the black box. The artificial intelligence suggests that you shouldn't drink now or something. So the patient will not believe that, because it's just artificial intelligence says, but it may be wrong. So we would like to open up those black boxes as much as possible, and this is what Dr. Seita was thinking, to combine the idea of data assimilation. We call it hybrid, because this is a data-driven evolution mode, and we have a regular data assimilation, taking data to adapt to the current situation of this person. And he's a medical doctor, and he thinks that this can be more convincing to the patients. So we have been working on this type of problem. So as I said, there are scientific paradigms evolving like this. At first, we studied from the experimental science, and then based on those experiments, we extract the basic theory that started the theoretical science. The theoretical science evolved as it is, but the computational science can produce even virtual experience. So that started the new paradigm of the science. And now it's the era of big data, or Internet of Things, or artificial intelligence. So we have a data-centric science. So that's something we get from the experience, and combined with the computational science. So that's the fourth paradigm. So now we are proposing that the next paradigm should be the predictive science. Okay, so thank you very much for your attention.
Do you think your methods can inform the climate modelers? Because you didn't talk about climate modeling at all, but it seems that the identification of good climate models could be something that this sort of big data problem could address.
Yes. So I think the next big advancement may be caused by merging the traditional approaches with the new machine learning or deep learning techniques. The climate modeling, that's a difficult question because we have not a good data set for the past long climate period. But we have imperfect model for the climate simulation. Then we can fill in the gap, the model errors, using the data that we have, so that even though we don't understand the process, we could create the process based on the data. So that's somewhat related to the hybrid or this human life problem. So we have imperfect understanding of the process, so we cannot derive the equation for what we don't understand. But we can derive, or we can get something from the data, so that can help improve the climate modeling.
Yeah, I would think that in the case of climate modeling, one of the problems is that you don't know what's going on in the deep oceans. Oceans are so important.
That's true.
And you don't really know a detailed state configuration of the oceans, especially in the past.
Right. That's true. So eventually, I think it's important to observe well, but without observation, we can play with those. We can make a lot of ensembles basically for different activities in the deep ocean. That will make the difference in the surface. If there is no difference in the surface, it's not important. But I think that it eventually comes up to the surface and makes a difference. So then we can understand the process based on many ensemble simulations.
Yeah, I mean, speaking of climate, it seems obvious to me that climate isn't a data assimilation problem because it's chaotic. There's no way you're going to get 100 years. You had trouble getting 30 minutes. But what you can do with this extremely powerful data set is to deal with the process studies. Although, when you were talking about this computer system, I suddenly remember this thing called the Earth Simulator, which I think was Japanese, right? And is this anything to do with it, or was it son of Earth Simulator, or which essentially meant all those things that we stick into, you know, vast 2.5 degree boxes or whatever they are in climate, you can actually crush it down to actually do something a bit more. And the thing that was interesting to me was when you're pushing it down to 100 meters, and finally you think, oh, that really might be genuinely cloud resolving with all of those things. But then you have to take those things back and put them into workable parameterizations. Yes. And that's where climate models struggle, essentially. Are the parameterizations actually realistic? Although you were looking at the 100 meter versus 250 meter, I noticed that you were saying, well, they're really quite, not too different, but actually they were quite different from the observations after 30 minutes. And when it comes to rain, the observations are right and the model is wrong, basically. So I think that the idea is that climate models have got to get the ensemble right. And so, I mean, are you actually running your ensembles at 100 meters?
Not the forecast, because we cannot afford. But the case of the rain prediction, it's too much to go back. But that case is the model error is the severe problem.
Yeah.
So we cannot get a good forecast at that resolution. The physics we use was developed for 1 kilometer resolution. Mm-hmm. We just make the higher resolution.
Yeah.
So the physics is not designed for that resolution.
But when we say physics and designed, we're really meaning parameterizations, right? We're not really meaning, you know, like F equals ma and fundamental physics. And so it's really addressing those issues that I think will, in the end, help. Yeah. Because real physics is real knowledge. Deep learning is stuff buried in a whole bunch of coefficients somewhere in some neural network that you don't actually know. It helped predict stuff, but you don't quite know why. And so kind of putting it all together and getting better physics that can then be scaled up to work in climate models, I think that is the way forward. And also will inevitably help, that's a good example there. I mean, they're fairly similar to each other, but they're nothing like the actual data. And that was after 30 minutes. So, and so addressing those issues in the model is I think, the thing that needs to be done.
I agree.
I think we have time for a couple of questions, if there are any more.
There is one online question from the remote audience. He's asking, the question is, assuming that CNN and RNN deep learning prediction system is well trained, the DL prediction will take only a few seconds. Then would it be necessary to have the 10K member ensemble data assimilation? Then it requires the fast supercomputer.
What's that? Okay. So the deep learning prediction is fast computationally. So 10,000 ensemble DA. So it's so 10,000 member ensemble DA is not deep learning.
No.
So it's a process-based model. So 10,000 ensemble members is just to explore what's the impact of having 10,000 ensemble members, and also what's the error structure that we can get. So that's a different goal for that research.
Yeah, he was saying that the goal was what? The wrong goal.
No, he mixed the deep learning prediction and 10,000 ensemble member research.
Okay.
Yeah.
Thank you.
Okay, I think we are running out of questions also, so let's. Thank you very much.
Thank you very much.